My name is Jacek Szymonek, and I'm a senior technology programmer at Techland. So if you haven't played Dying Light 2 Stay Human yet, I don't know what to tell you. It's a great game. It's a first-person, open-world, cooperative action game. The players take on the role of Aiden, a pilgrim looking for his long-lost sister and trying to survive in a broken, post-apocalyptic city. The title of this talk is Behavior Places, Breathing Life into the World of Dying Light 2 Stay Human. I joined Techland short before the production started, and during my 6 years in the company, I was part of a few teams. Initially, I worked on shipping the Linux port of Dead Island Definitive Edition and on the Nintendo Switch port of Call of Juarez Gunslinger. When I joined the project that became Dying Light 2 Stay Human, I started in the team that created the city builder tool, which you might have heard about. And after some time, I moved on to the AI team, where I took part in building the new AI architecture for CEngine. My interest naturally gravitated toward AI animation, so much so that I finally took over the responsibility for our animation technology stack. The agenda for this talk is as follows. I'll start by exploring the project requirements and motivation for creating a new technology. Then I'll explain what exactly behavior places are, and starting with a very simple example, we'll dive deeper and deeper into some of the technical aspects and decisions. We'll take a closer look at the animation graph and other assets. In the meantime, you will see how our animators and level designers work together to create the life in the city of Villedor. At the end, I'll tell you about the important parts that we've learned as a team and our plans for the future of the system. Let's start with the requirements that we faced for Dying Light 2. The city of Villedor is dead, mostly, except for the safe zones, the human settlements bustling with life, where life goes on almost as if the apocalypse had never happened. The survivors are building their homes and executing their day-to-day chores. You can observe them interacting with each other or with the environment using their tools. There is a massive variety of behaviors in here. The characters have their own agendas. They react to daytime changes. They randomly choose to act in different places. The perspective of the game is first person, which makes the locations tight in space. And the game can be played online, which makes it harder to achieve precise movement and animations. So what I've just described is the rough design for AI in our hub locations. And this is the narration that we wanted to convey. So to achieve it, we needed a technology for creating a huge number and variety of dedicated behaviors with precise animations, movement, and interaction with the environment. Here we've got some isolated examples of these behaviors. Reading a book, sweeping the floor, or being held hostage. These are the things that you might find our characters doing. So let's dive deep and see how we've built what you've just seen. The building block of a hub location is, of course, an AI agent. Our AIs are defined in terms of behaviors that they may execute. Let's take, for example, an AI with 4 basic behaviors of a melee fighter. This AI could find themselves in a hub location under the influence of the location logic. So if there are beds in the location and evening approaches, we would like to see this AI go to sleep. So it already knows how to walk to the bed, but we need to implement the sleeping behavior. Then let's say we would like for a fighter to go and sharpen their weapon. And again, we would have to implement that in the AI. Now, imagine that we would like to create 20 locations with 20 unique behaviors each. So this quickly amounts to 400 behaviors, each of them programmed separately, and most of them used in a single place in the entire game. As you can probably tell, this doesn't scale well. We need to figure out a different, more data-driven solution. Let's take a look at how we fixed this. First, we made an important distinction and divided the behaviors into 2 types. The ones we call generic can be executed anywhere in the world and are an integral part of every AI. Scripted behaviors, on the other hand, are usually tied to a specific location and can be used to interact with the environment. And in terms of scalability, the key difference is that scripted behaviors are defined outside of the AI. If we take a closer look at the behaviors, each one consists of some logic in code and the animation data specific to that behavior. As it turns out, when it comes to behaviors which are mostly used for narrative purposes, their logic is similar. We play animations in a particular sequence. There's nothing really gameplay related going on there, so that code can be easily extracted. The only important difference is the animation content. This allowed us to create a generic, data-driven behavior which may be executed in specific locations. We call these locations behavior places. Going back to our example AI, we've now managed to pack all the possible location-specific behaviors into one. It solved our scalability problem for the AIs. But we've opened a whole new can of worms by introducing new assets. Let's take a quick look at the asset workflow relating to behavior places. First, as programmers, created a special prefab, and we've introduced a new asset type called the behavior definition. These assets contain all the behavior configuration and animation data required, and they are created by the animators. The level designers, on the other hand, create behavior place entities by placing it in a desired location and choosing the desired behavior as a parameter. The entity uses the new asset we've introduced to parameterize the AI behavior. This way, animators can create the definitions in isolation, and level designers can then reuse them in multiple locations in the game. This is a screenshot of our level editor, and these colorful rings represent behavior place entities. So as you can see, a lot of them can go into a single location. They are also color-coded for different purposes. Some of them are used for dialogues, some for ambient animations, and other various reasons. So let's summarize. A behavior place in CEngine is an entity without any visible representation. It's configured with a dedicated asset called the behavior definition, and it represents the place where AIs can execute a location-specific behavior by using tailored animations and with rich interaction with the environment. Every AI in the game can either search for a place and decide to use it, or AIs can be requested to do so by external systems. Now that you know the basics of behavior places and how the users interact with them, let's dive deeper into the animation graph, the state machine, and its evolution. And minor disclaimer here, sometimes I'll be using the term animation graph and sometimes the state machine. However, in this context, they have the same meaning, and just like the diagrams. Let's look at a relatively simple behavior place example. In this clip, you can see a very simple sequence of animations. The character approaches a chair and sits on it. And then he's sitting for a while. He can loop once or twice, or maybe even more. But then finally, he decides to stand up. So that's 3 animations playing in sequence. Relatively simple, right? Here's how the animation graph state machine for that would look like. Sit on the chair, keep sitting for a while, which might loop, and then stand up. Let's look at another example. In here, we wanted to have a trader which can react to player proximity, encouraging them to buy something. The animation state machine for that BP for sure must be more complex, and it would look roughly like this. We start with the basic sitting loop, like we've seen before, an entry, and exit animation from standing and to standing. When the player is close, there is also another loop called trade. Well, we can't go directly from sit to trade. We need transitional animations in both directions. We need one for standing up and one for sitting down, just like you saw in the video. Entering those transitions is also guarded by a condition that checks character's distance to the player. So our machine got a little more complicated, but that is okay. It's defined in the behavior definition asset, and it can be dynamically injected into the main animation graph. When creating a new behavior definition, an animator would most likely choose one of the existing animation graphs as a template, clone the asset, and replace the animations with its own. And after about 50 different behavior definitions and graphs were created, we noticed that this approach does not really scale. So the graph structures, they were duplicated or very similar. We found 3 distinct patterns in the content with just tiny differences. And with that, our memory consumption grew really fast. Also, in the early stages of the development, we often also needed a way to apply a change in all graphs, which was a tedious job with so many assets. Because we wanted to support hundreds of behaviors, we decided to separate the graph structure from the animations. Instead of having many almost identical graphs, we tried to collapse them into one highly configurable one, generic. We were able to do that because our animation system lets us inject the animations into the states dynamically. So the animations used in a particular place were set in the definition asset, and it's created by animators. Let's examine how we were able to create the common state machine based on our previous example. The main state can be thought as an activity that the character performs while executing the behavior. And in this case, it is the act of sitting. That state is looped. Next, we need a way to get to the pose of the activity from the default pose, in this case, the standing pose. So during that animation, we enter the behavior place. Like the entry, when the behavior place finishes, we need an exit animation to the default pose. So what about the other example with 2 activities? The 3 states at the top we've already covered in the previous example. That's activity, entry, and exit. And let's look at the other looped state, the trait. Because it's looped, we can think of it as another activity. And what is left is these 2 states, which are transitional. They allow us to traverse between the 2 activities. So to make it clear, these 2 are still states in the state machine. It's just that their nature is transitional. There is still an actual transition that blends the pose from source state to the destination state. Since we are injecting in each animation just in time when it is needed, the 2 activities can become the same configurable state. We can collapse them. And then the same applies to the transitions. Let's position the states nicely. After all that generalization, we produce this state machine structure. And it revealed to us an interesting thing. And that's the key takeaway. A behavior place is represented by an animation graph that alternates between looped animations, called activities, by playing transitional animations in between them. Now only one question remains. How do we represent the configuration for this state machine? We know we've got these 2 activities, sitting and trading, and we can enter the behavior place from the external of the behavior place, standing pose, to the sit state. We can also exit from that state back to the external standing pose. We are also able to transition between the activities in both directions. And as you can see, our configuration can be represented as another type of graph, which we call the activity graph. In here, every element represents a dedicated animation. The activity animations are represented as graph states, and the transition animations as, well, graph transitions. These activity graphs are part of the behavior place definition created by animators. So at this point, you may look at where we are and think, okay, Jacek, so you had 50 animation graphs, right? Which was hard to maintain. And then to fix that, you pack them all into one Uber animation graph, which may still be configured by 50 different graphs. Like, what? How is that better? And it turns out that activity graphs helped us fix the biggest maintenance issues that we had. Let me give you one more example. Here we've got the state machine which contains 2 activities. This is our shopkeeper, who's either sitting or trading with us. Let's imagine that the shopkeeper sometimes falls asleep in their chair. And we may represent that with another activity called sleep. We also added these transitions that are required. We may represent that in the old approach, we would have to create the state machine, which would be probably used in one place in the entire game. And what if we wanted more activities? What if each activity could transition into another activity? We found this state machine to be too complicated and error-prone. We needed a better way to represent it. With the activity graph, we can extend the previous configuration with the new activity, sleep, and by adding the proper transitions. This type of graph is also much more constrained than the animation graph. For our purpose, behavior places, animation graphs had too many moving parts, and so activity graphs became easier to create and maintain. It's also much easier to validate and analyze the structure, which also became crucial for us, but we'll come back to that later. So let's summarize this part of the talk. During production, we've managed to create a common animation state machine for all behavior places, which is configured with lightweight activity graphs. These graphs allow us to express the state machine on a higher level and to minimize the memory footprint. Also, traversing a common, simple structure is easier to track and to replicate to other network peers. Remember that we also have to work in co-op. We also managed to decouple the behavior structure from the actual content, which made it easier to collaborate and create new assets. During the production, we've created thousands of activity graphs, which gave us the variety and the scalability that we were looking for. Now that you know how the state machine is built and what kind of animations are used in each state, I'll talk a bit more about the constraints that we've imposed on the animation that we've imposed on the animation content. We'll cover behavior place versus AI positioning, root motion, and navigation issues. Let's look at a simple example, a character approaching a chair to sit on it. There are two major poses in here, standing and sitting. With the entry animation, we can go from standing to sitting. However, before we start the entry, a character must approach a certain point in space. So what point exactly? Let's simplify our view. On the slide, you can see a blue line, which represents the nav mesh, and a black chair, which sits outside of the nav mesh. We'll break the action into two phases. First, we employ our movement system to reach a certain point. And then we will use the behavior place to do the interaction that you just saw in the video. Now, the character can only travel as far as the nav mesh goes, and then it must start executing the entry animation, during which they also move towards the chair, leaving the nav mesh. Okay, but what if the chair was moved further away from the nav mesh? What if it was rotated differently? If we execute the animation too soon in space or too late, we will not match the chair position. So should the level designer move the chair closer? But that's a lot of tedious work for thousands of chairs. So should we do that automatically? How do we validate that? Should we maybe add some fake unnatural motion to the character to make it match the chair? Or maybe the chair should always be placed on the nav mesh, but then it becomes a problematic obstacle when it is not used. So what if the entry animation changes to cover less distance? Do we have to move around all chairs that are placed on the level? So as you can see, the problem is not as simple as it might have previously seemed. So how do we solve it? Let's look at the situation from the top and simplify our view again. So with this symbol on the left, we represent the behavior place entity. For now, it's just a point with a direction in the horizontal plane. Whenever the AI wants to enter the behavior place, this is the only point that we've got. The character walks up to it and then starts the entry animation. This gray line shows us the root motion trajectory for the entry animation, and at the end of it is where the activity starts. We can see that the chair position is now correct because it will match our character's sitting pose. However, with this setup, level designers have two variables to account for. They must place both the PP and the chair on the scene, and then they need to place them relative to each other perfectly. And if the entry animation changes, one of the other must be moved around. Of course, this is too error-prone, and it's a huge maintenance burden, and we had to improve on it. To fix it, we figure out a different solution. What if we place the behavior place exactly where the chair is? The entry animation should now end at the behavior place position, which is synchronized with the position of the sitting. And to do that, we must calculate the point in world space where the AI is supposed to start the entry. We call these entry points. And they are calculated from the animation root motion and saved in the behavior place definition during asset compilation. Now let's add navmesh to the mix. The entry point lies on the navmesh, so the AI will be able to navigate to it and start the entry. So for situations where that is not the case, we've implemented a validation process which reports basically unreachable entry points. The level designer's task is now simplified to placing the chair wherever they like, placing the behavior place at the exact same spot, and making sure that the entry point lies on the navmesh. Of course, the entry animation can still change in such a way that the whole behavior place becomes unreachable without the level designers knowing. However, that outcome is much easier to detect than the characters sitting in the air or them being completely desynchronized with the environment during behavior place execution. There's another bonus to this approach. We can now have multiple entry animations in the activity graph. For example, we can have one approaching the chair from the left and one approaching the chair from the right. Then we can calculate entry points separately for each one. And with this data at hand, the AI can now easily pick which entry point it would like to use to best approach the chair based on the distance to the point or its orientation. Also, if one of the points is unreachable, we can simply pick another one. It's worth mentioning here that to aid level designers in the placement, we've implemented an isolated AI simulation in the editor, which is what you can see in the video. This turned out to be an extremely helpful tool. You can preview the AI enter the BP, the chair animating, and the calculated entry points. Let's look at a different, more complicated example with multiple activities. In this behavior place, we've got 5 activities, each one playing a simple idle standing animation. In the video, which is sped up, we can observe the transitions and the calculated entry point. As the behavior place runs, the character decides to move from the point of one activity to a point of another, and it will always move through the middle activity as defined in the activity graph. This is how it looks like in this example. Starting from the center activity, we can step in 4 directions to other 4 activities, and from each one, we can step back to the center. There is no entry and exit animations from stand to center. Since there is no need for a standing to standing animation, we can simply blend in. Let's recap. The simple structure of activity graphs allows us to extract root motion data from the animations during asset compilation. On the level, we set the stage in such a way that the entry animations start at pre-calculated entry points and lead us to the activity point, which may be outside of the nav mesh, otherwise unreachable. Exit animations must mirror the entry animations and must lead the character back onto nav mesh. With multiple activities, transitions may lead to different activity points, but we also must validate the root motion of a transition from A to B. It must be an inverse of the root motion from B to A. We also made sure that level designers' work is as easy as possible by implementing visualization tools in the editor, which was very crucial. Now that you know how we position the entities, let's talk about animating objects and interacting with the environment. We'll look at the different types of meshes animated in the place and how we set them up. First, let's go back to our example with the chair and let's try to extend it. We wanted to increase the feeling of interactivity between the character and the chair so that the chair is not just a static mesh. We'd like the character to grab the chair first, move it back a little, and then sit on it. So now the animation has been changed. It's re-imported to the engine, and now it has an additional track for the chair movement. Let's call that chair root motion. So how do we make use of it in the behavior place? First, every definition asset contains the metadata about the animations. We know that in this chair sitting scenario, the chair is now animated. So the animator adds that information to the definition. And they define a generic name for the animated item, like chair, and the name of the special animation track I mentioned before, chair root motion. The second piece of information is given to us by level designers. Knowing that we need the chair to properly animate, they save a reference to the chair entity in the special list inside the behavior place entity. When the character executes the behavior, we use that metadata. We tell the animation system to try to sample a transform called chair root motion and apply that transform to the chair entity pointed to us by the level designers. And this is what we call a bound animated mesh, because an actual entity binds to a declaration created by an animator. Okay, so what can go wrong here? Let's imagine that in the first frame of the animation, the chair position is slightly different than how the level designer placed it on the level. And if that's the case, the chair will be teleported from the position sampled from animation. And we saw that happening in the video. This is where the behavior place starts, and this is how the chair is initially positioned. So what do we do? Remember the activity graph I mentioned earlier? The same process that compiles the activity graphs also samples the initial transforms of all motion tracks. For example, our chair root motion. And we call those points mesh points. We use the data during world spawning to reposition the chair mesh. We make sure that it's standing in the right place for AIs to be picked up. And thanks to these mechanisms, characters always smoothly interact with the objects. There's no teleporting or sliding. Sometimes we cannot move the bound mesh from its original position. Take doors, for example, placed in the door frame. We only want to rotate or animate some part of them. So here the doors are opened for the first time, for the time of behavior execution, and then closed again. And for such cases, we can define an animated mesh, a special flag, which is called an anchor. Coming back to our previous example with the chair. If you place the behavior place entity here and then connected this chair to it, the chair would align itself to the behavior place. However, with anchored meshes, we do something different. Using the calculated mesh point, we are able to shift the entire animation space so that it matches the anchor entity. Now, the whole activity graph aligns to the anchor, and it doesn't matter where the behavior place entity is placed. Here's another demo of the doors. So we can move around the entity, but the animation space stays always anchored to the doors. The doors are not moved out of their frame, and they always are positioned very nicely. Not all meshes must be placed on the level. So imagine if we had to place every hammer, screwdriver, cigarette, or any small item on the level. That would be too much work. So that's why for small items such as these, animators can define what is called a spawned animated mesh. For such definitions, we simply spawn a mesh when the behavior starts and despawn it at the end. Other than that, we use the same motion track mechanism to animate them. They can also be, of course, attached to different bones of the AI. So let's summarize. When creating the behavior definition, animators add metadata about the required animated meshes. Selected entities bind to the animator's definition and they are fully controlled by behavior place. Meshes which are unmovable are defined as anchors, which aligns the activity graph to their position without moving them. Additionally, small meshes which are not part of the environment can be simply spawned for the duration of the behavior. So it's time to summarize this talk, share some lessons learned, and our plans for the future, for the further development. In this talk, you've learned about behavior places in CEngine. They are the building block of many different locations in Dying Light 2 Stay Human. They ended up being used as part of hub locations, bandit camps, open world encounters, dialogues, and spawn points. It's a scalable technology by which animators create location-specific behaviors to be placed by level designers. The system allows for massive variety in behaviors with as little impact on performance. It allows our characters to interact and become part of the environment, and it was designed for high precision in motion and positioning. We achieved that using custom compiled asset type and by thoroughly analyzing the animation motion data. Here are the most important things we've learned. The content must be strictly validated if you want to achieve high precision. We had cases where there was only tiny amount of root motion in the looped activity animation, which caused the entire animation space to rotate 90 degrees after a couple of minutes of gameplay. So after like 20 loops, the whole thing rotated. To achieve great performance, you must use offline processes. We could build the activity graph during the game, but we would need to load 5 animations just to sample a few transforms. Next, specially tailored tools for content creators are extremely important. You can create the best and smartest feature or system, but without the appropriate tooling, it may as well become useless. Tools can show the content creators what are the possibilities of the system, and they also help automate mundane tasks. Lastly, make sure to always iterate the system with the users. Behavior places went through 3 major iterations with data conversions and stuff just to get there. And as always, try to keep things simple and avoid over-engineering. Let's close with our plans. We'd like to have a single behavior place that can animate more than one AI. We'll be also focusing on traversal using behavior places, which we've managed to accomplish in some quests already, and also managing animated meshes. We'd like to be able for an AI to pick up an item in one place and put it down in a different one. And that's all. I'd like to invite you to the Techland booth tomorrow. There's people from all departments chilling there, so if you'd like to join us and work on some cool new things or maybe just chat a bit, there we are. We also have a cool juice bike, if you're into that. And now I think we've got time for some questions.
You briefly mentioned interaction between multiple characters, and in this game, was there some kind of situation that you handled multiple character interaction in a different way? Because, as you said, you don't have like tool which is extendable and usable for those kind of stuff. Was it that scripted, or how do you handle that?
So to be honest, we started 2 behavior places with 2 AIs at the same time, and but there was one caveat with that. It had to be the simplest behavior place of all. So the number of loops had to be synchronized. The configuration had to be very similar. It wasn't really validated, so it was kind of risky stuff to do for the content creators. But we've managed to do it, and I think it works nicely. So yeah.
Thanks for the talk.
Action like look at and the reaction to the player that stand nearby was handled by the system, or it was a separate system, separate modifier for the animation?
So the reaction...
Like a look at, you approach to the NPC and NPC turns head to you to get noticed.
So the look at is, it's a different thing. It's handled by a different system, and it's layered on top of what is happening with the full body, right? So the behavior plays is full body, but then we could enable the look at. What is interesting is that in the definition, animators can also declare whether they would like for the look at to be enabled at all or not. So for example, if you're in an extreme pose of, for example, laying, or this is a sleeping behavior place, they just go, look, we don't want no look at. But for most of the places, or for the shopkeeper especially, the look at was simply enabled.
Hi, thanks for the talk. So I didn't really understand what was the problem with placing the chair actually inside nav mesh.
Okay, so like I said in the beginning, since the game is first person, it also influences the level design a lot, right? So all the locations that we had, they were very tight. There wasn't really much space to place a lot of props. So like if you wanted to place 5 chairs, cool, but then you took half of the nav mesh, right? And these chairs are static, right? So the nav mesh would have to be cut out around them. And that limited the amount of movement that we could do. Like it was limiting for the player, and was limiting for other AIs traveling from one spot in the hub location to the other. Does that answer your question?
Yeah, I guess. Thanks.
I'll hang out after the Q&A for some time, so you can catch me. We can talk about it.
So you've mentioned briefly that initial system had memory problems, but what are those? What is the source of those problems?
The initial system. Okay, so initial solution that we had didn't really scale in memory. That was one thing, and the other thing was the cooperation was not easy. So for example, we had a lot of behavior places saved in one asset for various technical reasons that are not worth going into. But that was one thing that influenced us into doing this whole trick with generalizing the graph and then configuring it differently.
Thank you.
Thanks for the talk. I believe you briefly mentioned that the system had to work with a multiplayer. And my question is, how did it work with a multiplayer?
Yes. Okay, so the 4 states that I showed you in the main machine, for multiplayer, they are collapsed basically to one enum. And we replicate that enum, so that state, so is this AI and there's also activity ID, right? But then, so if the AI in host is an activity, and this particular activity, we send that, and the other peer synchronizes with that, exits their transition. Sometimes we skip some states. So, for example, we can skip the entry animation if we have to, quickly synchronize, and that's the thing, that we didn't have to replicate anything from the graph. We only tracked the current state, like the main state, because you also blend with things. But then you only track the main state, replicate that, and try to do some shortcuts to traverse the graph.
Thanks.
All right, I think that's it. Thank you.